Today I'll talk about material derivative or substantial derivative, and then I'll talk about acceleration. Material derivative in fluid mechanics. The position of particle A in a fluid field at a time t is given by coordinate x, y, z. The velocity component of the particle are denoted by u, v and w and can vary both position and time. That is, u is nothing but x, y, z and t, v of x, y, z of t and w of x, y, z t. Now, velocity change over time. At a later time t plus delta t, the particle moves to new position b, that is x plus del x, means position of the particle, x plus del x, y plus del y, z plus del z, and the new velocity component are u plus del u, means change of the velocity, v plus del v and w plus del w. The velocity at new position after time del t are given by u plus delta u can be written as u of x plus del x, y plus del y, z plus z del z, t plus del t, and v plus del v, that is equal to v of x plus del x, y plus del y, z plus del z and t plus del t, and w plus del w will be w of x plus del x, y plus del y and z plus del z and t plus del t. Now, if we expand each component using Taylor series, so u of x plus del x, y plus del y and z plus del z and t plus del t can be written as u of x, y, z, t, then partial derivative of u with respect to x into del x, partial derivative of u with respect to y into del y, partial derivative of u with respect to z into del z, partial derivative of u with respect to t into del t. Similarly, we can write v as well as w. So v will be v of x, y, z, t, partial derivative of v with respect to x into del x, partial derivative of v with respect to y into del y, partial derivative of v with respect to del z into del z, partial derivative of v with respect to t into del t. Similarly, w of x plus del x, y plus del y and z plus del z plus t plus del t, we can write w of x, y, z, t plus partial derivative of w with respect to x into del x, partial derivative of w with respect to y into del y, partial derivative of w with respect to z into del z, partial derivative of w with respect to t into del t. So these are the Taylor series expansion. Now the change in velocity over del t can be expressed as, means del u the change of the velocity. So this is new velocity at point b and the old velocity at point a. So u of x plus del x, y plus del y, z plus del z, t plus del t, del t minus u of x, y, z, t. Similarly, del v and similarly del w. So this is the change in velocity over del t. Now we already did the Taylor series expansion of this. So u of x plus del x, y plus del y, z plus del z, t plus del t minus this is the new position velocity and old position velocity minus that is the change of velocity, that u of x minus y minus z plus t. If we do that, so ultimately we will get that partial derivative of u with respect to del x, partial derivative u with respect to x into del x, partial derivative u with respect to y of y into del y, partial derivative of u with respect to z into del z, partial derivative of u with respect to t into del t. So similar way we can write v as well as w. So this is the change of velocity. Now change of velocity by del t means what will be the change of velocity with respect to t. So the change of velocity by change of time. So this is the old new velocity minus old velocity by del t. Similarly, del v by del t, del w by del t. Now if we put this value, so we'll get that partial derivative u with respect to x into del x by del t, partial derivative of u with respect to y, del y del t, partial derivative of u with respect to z, del z del t, partial derivative of u that is partial derivative of u with respect to t, del t by del t. Now here, now means this is nothing but del u by del t, that I am written here. So del u by del t, so that the del u by del t, del v by del t, del w by del t is nothing but this. Now here del t will be cancelled out, and we know that u is nothing but that change of position by change of time. So that del x is nothing but u by del t. So we can plugging this value. So del y is nothing but v into del t, del z is nothing but w into del t. Now if we plug this del x, del y and del z here, here, so finally we'll get, so del u by del t is nothing but partial derivative u with respect to x, so u into del t by del t, partial derivative of u with respect to y, v into del t by del t, partial derivative u with respect to z, w into del t by del t, and we know partial derivative of u with respect to t, del t by del t. Now here del t will be cancelled out, here for v, del v by del t also similar way we can cancel out. So finally we'll get del u by del t is nothing but u into u is here, so partial derivative of u with respect to x plus v into partial derivative of u with respect to y, w into partial derivative of u with respect to z plus partial derivative of u with respect to t. So we'll get del u by del t is this. Similarly, so del v by del t, so only u will change and that will comes v here, and del w by del t. So we'll get that. So change of velocity is nothing but this. Change of velocity with respect, change of that y velocity is, sorry, u velocity, u by del t, del u by del t is this, del v by del t is this, and del w by del t is this. Now if we take that dt, del t tends to 0, so we put the limit, so that becomes, so that is new velocity by old velocity by del t, so del t tends to 0, so that is limit del tends to 0, del u by del t, so that we can write capital du by dt, that we can write. So that is actually called material derivative, and we can write dv by dt, so that is also material derivative, so that is limit del t tends to 0, del v by del t, and dw by del t, that is limit del t tends to 0, so that is that component velocity w at new position minus component velocity of position a of w, so we get that capital du by dt, capital dt, capital dv by capital dt, capital dw by capital. So and we know this value from that earlier slide. So now we plug, we'll get capital du by dt is nothing but u into partial derivative of u with respect to x plus v into partial derivative of v into partial derivative of u with respect to y, w into partial derivative u with respect to z, partial derivative u with respect to t. So that is du by dt is nothing but this. So that is actually, and similarly we get capital dv by dt, capital dw by dt. Okay, so we'll get that material derivative. So this is x component, y component and z component. So that is nothing but that acceleration. This is actually change of velocity by change of time, that is actually called acceleration in that x direction. So that is, in the acceleration is a vector, that x component of acceleration is ax, so that is nothing but this total term. So this total term we can write that partial derivative of u with respect to t, and this we can write as a vectorial component, so capital U dot del u. Similarly I can write ay and Az. So here that will be equal to Az is equal to dw by dt. So we will get that component acceleration. So here that capital U is nothing but U, V and W is the velocity field, and capital this is del or nabla U, V, W, that is represent the gradient of the U, V and W. So here that this term that partial derivative of U with respect to t and partial derivative of v with respect to t, partial derivative of w with respect to t. So these are the local velocity, so change at a fixed position, and this is called local acceleration. And u dot nabla u dot another here, that is, this is a vector, so capital that actual velocity, so that is u dot, I mean it's vector quantity of velocity into dot nabla v and u dot nabla w. These are the convective derivative, so these are the convective term, and that is change due to movement through the velocity field and also called convective acceleration. So these are the convective acceleration, and this term is actually local acceleration. Now that velocity and acceleration, so the velocity vector in the fluid is given by, you know, that u, that bold u is ui plus vz and wk. So u, v, w, these are the component of the velocity in x, y and z direction. Now we can write the acceleration of the fluid particle, that is bold A, so that is nothing but capital D and bold U by capital D. So that actually capital du by dt I, capital dv by dt j plus capital dw by dt k. So this is nothing but acceleration of ax, this is nothing but acceleration of ay, this is nothing but acceleration of in z direction. So acceleration A is nothing but axi plus ayj plus azk. So ax is nothing but capital du by dt, ay is nothing but dv by dt, and capital az is nothing but capital dw by dt. Now we already know capital, if we plug all these value, so ultimately we'll get so capital du by dt is nothing but this term into I, this term into j, and this total term into k. Now if we segregate I, j and k term individually, we'll get and we know we will get, if we segregate I, so ultimately we'll get this. So capital D by capital bold U by capital dt is nothing but partial derivative of partial derivative of total u by t. Similarly, u into partial derivative with respect to that u vector by with respect to x. Similarly, in that v direction and w direction. So we can write, so here in that expanding the convecting term, so capital U, so not capital U, that vector quantity of u dot nabla into nabla, then vector velocity, that we can write like that way. So ultimately, so that acceleration we can represent in the vectorial form. So that is, this is the acceleration, so that is capital D by velocity vector by capital dt. So that is nothing but partial derivative of velocity vector with respect to t, then u dot nabla in, and then u, where u is nothing but ui plus vj plus wk. So that way we can write the acceleration. So acceleration is axi plus ayj plus azk. We write in the material derivative of substantial derivative, with this. So capital du by dt I plus capital dv by dt j plus capital dw by dt k. Okay, so now from here we can easily calculate the acceleration when the particle move from position A point to position B. So that is the acceleration in fluid flow as well as the material derivative and substantial derivative. Now here ax, ay and az are the acceleration in the x, y and z direction respectively. This formulation is crucial for understanding and predicting the behavior of the fluid in motion. So that this is the foundation of Navier-Stokes equation. So that's it.